Very good afternoon. This one will be the last lecture of day 2 of this ongoing 5-day GAN course. The topic for this last lecture is target detection technologies, which will be delivered by again Professor Naoki Shinohara. Without any further delay, I invite him to start the talk.
Yeah, thank you so much. So welcome back again. This is our last lecture today. We have last 3 days more. Thank you so much. And so today you've already learned how to increase the beam efficiency, just the receiver in front. So now you can design, you can optimize the beamform or the antenna technology for the receiver in front. And in this afternoon, when this target moves, you have already learned how to control the beam direction. So now you can design the beam controlling antenna system based on today's lecture. But additionally, we need important technology because now we cannot understand where the target is with help of the phased array technology only. So we need technology of the target detecting where they are. So this is the other important technology for the radiative WPT. So in this 1 hour, I'd like to introduce this target detecting technology. And especially, there are a lot of technology of the target detecting, but mainly I'd like to introduce a special technology for the wireless power transfer. And these are typical technology how to detect the position of the user. Of course, optical method is useful. Now we have AI technology or the other. And someone consider GPS, we can use it. And supersonic for the golf player, the other, they use supersonic technology. But so of course we can use this target detecting technology. But I think they are not the best. I'd like to introduce later. And the other technology is a closed loop from the receiver information. And when we control the beam direction and the receiver, if the power is not enough than expected, so the receiver transmits information, power is not enough, and transmitter consider our beam is not optimal. So we control the beam direction and we make a closed loop. For example, this is the other way. And we can use the pilot signal, radio wave itself from the user to check the position. So in order, briefly, I would like to introduce the target detecting technology. And at last, mainly I would like to introduce this retro-directive technology because this retro-directive technology has a merit for the wireless power transfer. In order, so this is a typical technology of the optical method. So I would like to introduce some example of the wireless power transfer demonstration. Again, you show the MIRAX experiment in 2022. At that time, we installed the phased array antenna, as I mentioned, and we can control the beam direction. But we didn't know where they are, where the airplane are. So for the target detecting, this is a movie from the 2 cameras. And based on this algorithm, 2 camera means we can detect the position, not only the position of the targeting by the optical method, but also the depth or distance between the transmitter and the receiver, like our 2 eyes. So in this case, like this figure, we can detect position of the this airplane and height of the airplane by these 2 CCD cameras. So we succeeded in this MIRAX experiment about 30 years ago. And recently, my Masako student carried out the other target detecting by the image processing. now this mechanical moving antenna chase this airplane. And in this case here, on the screen, we catch the position of this airplane, and we calculated the position of this airplane, and we control this target, this antenna moving. So this is a very simple image processing target detecting. So here you can see we can chase this position of the airplane by the image processing. So we succeeded to provide the wireless power to the flying small airplane in this case. And next, I would like to introduce a closed loop. And so this is a very, very famous Japanese technology named rotating electromagnetic vector method named REV method. So originally, as I mentioned, we control the phase of the phased array antenna, and after transmitting the radio wave, all radio wave is merged into one. And so we can explain it by the help of this merge of the vectors. And in each different phase radio wave merged into one. And in this case, after receiving the receiving power, this total power is informed to the transmitter, and we found this power is not enough. And in this case, in each antenna element, they rotate the phase from 0 to 360 degrees. And when we rotate this phase in one antenna, we find one best solution to increase the received power. And when we find the peak power with the best phase, and we change the other antenna, and we rotate the phase again, and again and again, totally this phase creates only one line. So this only one line vector means received power will be maximum. And this is proposed by the Japanese company Mitsubishi Electric. And usually they apply this technology to estimate the error check of the phased array antenna, usually, not for the beam controlling system, but sometimes they apply this REV method to control the beam direction. But based on this theory, we have to rotate the phase in each antenna. And if we have, for example, 100 antenna element or 1,000 antenna element, we have to rotate the phase 100 times, 1,000 times. So unfortunately, it's very slow system. So they apply this REV method mainly to check the initial status of the phased array antenna, not to control the beam direction. But this is a very interesting closed loop closed loop method to control to check the target position. And Canadian group revised this REV method. Exactly meaning not revised, but they propose the other closed loop technology for the Canadian airplane experiment in 1987, and they add the altitude measurement system, and with help of the distance data, altitude data, they only change the two phase in each antenna only. Compared to this REV method, they control the all phase from 0 to 360 degrees. But in this sharp method, they only control the two phase only, and additionally they add the distance data. And based on this equation, they can find the optimum power by change of the two phase in each antenna. So this is named the sharp method. And this is only one example for the SHARP experiment in Canada in 1987. And recently, we Kyoto University proposed the new method of the other closed loop named PAC, position and angle correction method. This is a collaborative research result with Kyoto University and Mitsubishi Heavy Industry in Japan. And in this PAC method, we use a similar closed loop. And in this PAC method, it involves the data of the shape of the antenna, like this. If antenna shape is strange, even if we know the target position, we cannot control the beam direction because we have to control the optimum phase in each antenna position. But if we don't know the shape of the antenna, we cannot control the exact beam. So in this PAC method, based on this algorithm, we can detect the target of each panel, each antenna position, and finally, we can control the beam direction with the optimum direction and optimum phase in each antenna. So this is the result. If we don't apply this PAC method, beam directivity of the beam form is very straight. But after this closed loop PAC method, we can create the optimum beam, for example. So this is a closed loop method. And of course, some of you know, we have a target detecting technology named direction of arrival by the transmitting radio wave somewhere. And this DOA method, if we have, we know the target detection or direction of arrival, and we have a good physical technology. So if we have a direction of arrival, we can control the beam direction. And we named it, compared to the hardware retrodirective, we Kyoto University named it a software retrodirective. Because in this case, we use a pilot signal from the users. And this is a very basic theory of the DOA, target detecting with a pilot signal. It's very simple. At least we use a two receiving antenna for the pilot signal. And when the pilot signal is transmitted from somewhere, this direction, this radio wave from anywhere to the transmitter, these two antenna receive the different phase. So if we can assume the plane wave, it's far field, it's easy to calculate this rectangular shape, the direction of arrival. This is a very, very simple basic method, but it contains some errors based on the signal noise ratio, etc. So this is a error of the target detection based in consideration of the signal noise ratio. And if this SN ratio is very high, error of the target detecting becomes very high. And if SN signal ratio is very low, so we can suppress the error. But still, we have some error to detect the direction of arrival in this case. So we have some very good algorithm named beamformer Capon linear prediction LP, or most famous DOA algorithm is music, multiply signal classification method, or ESPRI method. These two, music and ESPRI method, we can detect multiple direction of arrival. And this basic method cannot detect two or three multiple pilot signal. But in this, with music and ESPRI, we can detect multiple target detecting direction of arrival. So if we have this good technology of the direction of arrival, and after detecting the position or direction of the target with help of the phased array antenna, we can control the beam direction. But it contains one big problem. control speed, target detecting speed. Compared to the REV method, is better. But to suppress the error of the detection of arrival, these algorithms are very complex. So we need some time to detect the direction of arrival in these algorithms. So if a user moves with very high speed, we cannot chase the high-speed moving target in this case. So of course, we can apply this DOA algorithm if we have enough time to detect the time. But I recommend the other method later. And so sometimes we, Kyoto University, propose the revised new DOA direction of arrival method in combination of the DOA matrix, near field DOA matrix, and Esprit method. And so because usually, so as I mentioned, so original target, this target DOA method is with the assumption of the plane wave only. But as I explained in the morning, so we would like to put the receiver in radiative near field, and it means we cannot assume the plane wave in this case to increase the beam efficiency. So in this case, like a sharp method, we need to estimate the distance between the transmitter and the receiver. So in this case, we had the other algorithm named the near field DOA matrix. But this was not enough, we think. So we add the high accurate DOE matrix named Esprit, and to detect the distance, we merge the near field DOA matrix into one. So based on this technology, we can estimate the both direction and distance quickly. So, but I don't have enough time to explain these algorithms all. So let's move to the last one. This analog phase conjugation circuit and a retrodirect system. So to keep the high beam efficiency on WPT, accurate target detecting is not only required, but also required recognizing the position of each antenna, as I mentioned. Of course, it's easy to assume we have a very rigid antenna. And from this start point of the rigid antenna, we can control the beam direction. But sometimes antenna is not rigid and like a very soft structure. And in this case, we cannot detect the start position at the transmitter. So in this case, target detecting, only the target detecting is not enough. And additionally, we'd like to detect the position of each antenna on the transmitter. So in this meaning, this retrodirective technology is best for the wireless power transfer, any case. And from here, I'd like to introduce mainly this retrodirective technology. This is originally from the corner reflector. So maybe you know, if we have a mirror, and when we receive the sunlight, and so reflected sunlight is converted to the other way. So this light. It means in this case, if we have only the mirror, all phase keeps the same same value, and same phase creates this on contrary beam detection. But when we put the other mirror with a vertical line, this reflection occurs double. As a result, this incoming signal or incoming solar ray go back to the detected position. This is the original method. And the scientific giant Van Atta proposed this Van Atta ray. this corner reflector is theoretically perfect, but this is still complex, and this is a very strange shape. So with help of the array antenna technology, Van proposed this structure. We put, this is a one-dimensional example, and we put each antenna here. And if this is the same as a mirror, when we receive this antenna array, and next at the next antenna array, we receive this, for example, minus phi phase shift, and next -2 phi and -3 phi. And if it is just a mirror only, this phase difference keeps, and the result 0, -1, -2, -3 creates this line. So Van proposed we change the position from the receiving antenna to the transmitting antenna. And when we change the position from the edge of the right side to the left side, we change all phase relationship. And for the transmitting signal, when we change the position of the each phase difference, as a result, this transmitted radio wave propagates into the transmitted phase. So this is named the Van array. Though in this case, we connect each antenna, symmetry antenna in equal antenna length. So this is a very simple retrodirective array. But in this case, it's not easy to apply the two-dimensional array, and it's not easy to develop the amplified circuit and the other. So the other people, I don't know who developed it, but they create the similar relationship with the incoming signal on the transmitting power with help of the mixer and the local oscillators. We put the mixer in each antenna, and we put the local signal, and the frequency is a double of the incoming signal. And in the mixer, this local signal and the incoming signal will be merged and multiplied. And in the next figure, I will explain the formula. But as a result of the mixer with the local signal, double frequency, and the incoming signal, same relationship of the incoming signal and the transmitting signal are created. And as a result, this automatically we can transmit the microwave power to the detected target position. So this is a retrodirected system. And based on this explanation, I will introduce the calculation. So in the mixer, we can multiply two signals. And here, as I mentioned, we have a local signal. Now we assume that any frequency as a local signal here. And in each antenna, we receive the different phase incoming signal here. And in each mixer, two signals will be multiplied. And with help of the equation, we can convert this multiplied signal to the summing signal. And here you can see we have two different signals and two different phases incoming. And here you can see the same phase difference with input signal. But here we have the minus phase difference from this multiplied signal. And after the passing the low-pass filter, we eliminate this component, and we get this signal only. And when we assume the local frequency will be double, and at last this different frequency becomes the same frequency of the incoming signal here, and we get the minus phase changes. So here you can see in this antenna, for example, with help of the mixer and local signal with double frequency, we get the plus signal from the minus signal, or minus signal to the plus phase difference. So as a result, we can control the beam direction. And so merit of this retrodirective antenna is to detect the antenna position. And we don't mind any antenna position in this retrodirective system, because in this case, this phase difference includes the position difference of the position of the antenna element. So when we put the antennas in rigid antenna, this figure is a very good explanation. But if antenna position is different, like this figure, but different position of the antenna involve the different incoming signal phase. So as a result, even if we don't know the shape of the antenna, this retrodirective system can create the best beam form to the receiver. So this is the best technology. It involves target detecting and antenna position detecting, and additionally, there is no phase shifter. So in this meeting, it's not a phased array antenna. This is just an array antenna. There is no phase control system. So in this case, we cannot control our expected beam form, but automatically we can create the microwave beam from the pilot signal. It's not a phased array antenna, but it's a retrodirective array antenna. And this is a typical beam pattern. This is a measured beam pattern. When I was a PhD course student, and this is a typical beam form. And when retrodirective on, this beam form move to the target. So as a result, this beam pattern is created. So always this beam chase the target. So this is the original beam pattern by the phased array antenna, and this is the typical beam pattern with the help of the pilot signal of the retrodirective system. And here you can see the peak power is not equal. So here some power decrease. So please remember the first lecture in this afternoon. In the phased array antenna, beam pattern can be calculated by the combination of the element factor multiply array factor. So this retrodirective pattern erases the array factor, because this beam chase the target. But this beam pattern keep element pattern, one antenna beam pattern itself. So this is just the same as the element pattern itself. For example, one microstrip antenna or dipole antenna itself. So this is the other evidence for the phased array antenna theory. So this is a very interesting measurement data of the retrodirective system. And so retrodirective system was originally not for wireless power transfer, but for the wireless communication system. So because if we have a retrodirective system, radio wave beam chase the user. It means we can develop very secret wireless communication system. Antenna gain moves only to the user, moving user, and outside of the user, even if the user moves to the other side, the other point, the other user cannot receive the enough power to receive the information. So in a lot of university, so they developed a very interesting interesting retrodirect system for wireless communication. And this is most easy to understand how to develop a retrodirect system. Here is a mixer. And here is a incoming radiative line. And here we put a local signal with a double frequency. And we divided this local signal to each mixer. And we mix the two signals of the local signal and the incoming signal. And from this line, we create the phase conjugation and total, at last, this radio wave chase the target. So these are very interesting, all developed retrodirective system. So we have a merit and demerit of the retrodirective system. Merit of the retrodirective system, I explain now, both target detecting and recognition of the antenna position. It's very good merit. And it's very high-speed beam controlling system because these are just analog phase conjugation circuit only. There is no phase shifter, there is no target detecting algorithm or the other. So it's very high-speed beam control. And additionally, very low cost without expensive phase shifter. But there are some demerits of the retrodirective system. So beam forming to user only because there is no phase shifter. So if there is no incoming pilot signal, this retrodirective array cannot transmit the power. So this is a big demerit. In the retrodirective system. And there is an interference between the signal, pilot signal, and the WBT beam. So theoretically, as I mentioned again, so we must use the same frequency in the incoming radio frequency and the outcoming microwave beam. So it's the same. It's the same frequency. Frequency of the incoming signal is omega RF, and microwave power is in the omega RF. It's the same. So in the same media, there is two different signals in the same frequency. So interference occurs because microwave power beam is very high. So this is a very big demerit. And fluctuation of the pilot signal source and the WPT signal occurs the error of the phase difference. So this is the big problem because source of the pilot signal at the receiver and the source of the local signal is at the transmitter. So if these two signal source is fluctuated, so this fluctuation becomes creates the phase error. So this is the problem. And this is the most important demerit. We need extra power source as a receiver to transmit the pilot signal. So someone asked me at that time, so we would like to drive the IoT sensor without any battery. But in this case, we need a special battery to drive the pilot signal. So as a WPT system, it's better or worse. So this is as a demerit. But we are engineers, so we know these demerits. So we have already developed the very revised retrodirect system in consideration of these demerits. So for example, to suppress the interference between the pilot signal and the hyper microwave beam, in Kyoto University about 20 years ago, one professor proposed the pilot signal with a spread spectrum modulated pilot signal in the transmitting weak power signal. And if we add the modulation like a spread spectrum, and even if we have the same signal in the same frequency band, modulated signal and a very peak microwave power, we have a demodulator in the transmitter, and we can divide this peak continuous wave and the spread modulated signal into two kind of the signals. So we proposed it and we carried out an experiment. And when the power of the pilot signal is very weak, unfortunately, a phase error occurs. But we add the band element filter and we suppress the microwave power into the pilot signal receiver, and we can reduce the phase error for this retrodirected system. So this is one interesting approach to suppress the interference between the same frequency pilot signal and hyper microwave beam. And my boss, Professor Hiroshi Matsumoto, before I joined this laboratory, he proposed the other retrodirective system with two asymmetric pilot signals. So here you can see the block diagram to create a phase conjugation. At first, they use two different asymmetric two-pilot signals from here to here. And with help of the frequency double or double mixer, and at last, we get from the minus theta phase difference in each antenna as an incoming signal to the plus theta as a microwave power. So in this case, pilot signal frequency are different from the microwave power. So we can suppress the interference with a pilot signal and hyper microwave in this case. And the other US group proposed to solve the other demerit of the pilot signal fluctuation in each pilot signal source and local signal. So they adopt the incoming signal as a local signal. So in this case, there is no signal source in transmitter. And from here, they receive the pilot signal, same pilot signal, and they create a double frequency. And they apply this double frequency pilot signal as a local source, and it's the same as the original circuit. And in this case, there is no independent signal source. So if signal of the pilot signal fluctuates, simultaneously local signal fluctuated. So as a result, there is no error in this system. So this is a very interesting retrodirective system without local signal. And before knowing this interesting US research, I developed the other combination retrodirective system both to suppress the interference and to suppress the fluctuation of the independent signals. In this case, I adopted the pilot signal as a 1/3 frequency of the microwave power. And with combination of these diagram, we create the original frequency and phase conjugation. And in this case, we use the pilot signal as a local signal. So we can suppress both interference to the signal, weak signal, and to suppress the frequency the fluctuation in independent signal source. So when I started my research life as an assistant professor, I developed it with help of the Japanese companies. And recently, so most important demerit, we need an extra power source in the user. So recently, we Kyoto University proposed the interesting retrodirective system. As you know, of course, we have the rectenna receiver at the users. And we transmit the microwave power, and this rectenna creates electricity. It's a system. But in the rectenna, so there are some reflection occurs at the higher harmonics or the other. So theoretically, because it involves a diode. So at first, we transmit the microwave power to everywhere, for example. And when this user with rectenna receive this microwave power, and of course, this rectenna can create the electricity, but simultaneously, some harmonics occurs and is re-radiated. So we propose we reuse this harmonic re-radiation from the rectifier as a pilot signal. So in this meaning, at the receiver, at the user, there is no extra power source. They have only the rectenna to receive the microwave power. And this rectenna creates automatically pilot signal. So we propose it, and we carried out the experiment. And additionally, in this case, this pilot signal is very weak, so we revise sometimes the mutual coupling between the high power and the local weak signal. So with change of this technology, and we receive the pilot signal and the microwave power in the oscillator, and at last we can create the phase conjugation from the harmonics, re-radiated harmonics to the microwave power. So this is a demonstration movie. Here we put the antenna only with help of the receiver, rectenna. And when we control, so we need, and when we move the user, this here you can see the evidence of the power received, and we change the position of the receiver without any extra power source. This is our recent proposal by Kyoto University to reduce the demerit of the retrodirective system. So now there are a lot of interesting retrodirective systems. And additionally, so these examples are only a one-to-one retrodirective. Theoretically, it's easy to understand. But if we have a double power, a double user, or multi-reflection, etc., and at the transmitter, when we receive the merged reflected signal or some multiple user signal, what happens? We can create the exact power beam by only the merged pilot signal. I have some doubt. So I try to understand how to drive the retrodirective in march pass or MIMO, march out retrodirective situation. This is original patent by OCR Corporation. This is a US startup company. They propose this march pass retrodirective system when the pilot signal transmit everywhere. And with help of the march pass direction, this transmitter of the retrodirective can recreate this march pass signal. They said in their patent, but I had some doubt theoretically because received pilot signal are merged from the march path. So how to recreate the same march path? So we simulated exactly by help of the microelectromagnetic computer simulation. And we put one receiver as a transmitter of the pilot signal. And this is a transmitting array. And we put a wall, perfect conductor. And in this case, the pilot signal reaches at the receiver through this direct path and the reflected path. So what happened? This pilot signal are merged at the receiver. So if there is no retrodirective, this is an optimum beam, just in front beam only. But when we receive the pilot signal and directly we recreate the phase conjugation through the merged pilot signal. And as a result, so exactly we can recreate the direct path and the reflected path. So I was very surprised. We can recreate the same beam form from the march path pilot signal. So some antenna professor explained me, antenna is the same as a transmitter and a receiver. So theoretically, there is no doubt. My friends told me, but I had some doubt. So I checked this computer simulation, but here you can see we can recreate the direct path and the reflected path only by the French conjugation circuit from the merged pulse signal. So this is a very interesting retrodirective system. And we can apply the safety system. If we put the eliminator, human being itself, inside the path, direct path. In this case, there is no path of direct path from the transmitter to the receiver. And this reflected path only. And in this case, what happened? But in this case, pilot signal is only one. So it's easy to understand. We can avoid the human being itself. So if there is no retrodirective, and if we know the position of the receiver, we create this direct beam, and all power go into a human body, and it's very dangerous system. But if we have this MIMO retrodirective system, we can avoid the human being. So this is a very interesting system. And we expand the multi-unit retrodirective system. These technology are only one pilot signal source and in multipath. But next, we apply the multi-device retrodirective system. For example, we put a two signal source. And in this case, compared to the multipath system, multipath pilot signal are related because signal source is the same. Difference between the direct path and the reflected path is only a difference of the path length. But in this case, we have two different signal sources. What happened in this case? At the receiver, we receive the same merged pilot signal. So we tested this simulation. As a result, we can create double beam only with help of the phase conjugation. So I also was very surprised. But antenna professor, my friend, told me it's natural. So, but even if we put a multi-user, we can apply this retrodirective system. And we compare this multi-user retrodirective, and we control the TBD, time division beam form, and etc. And totally, retrodirective system are better than the other beam control system. And more, we go to university at the concept of the amplitude configuration, because as I mentioned again, we would like to put the user at the radiative near field distance. And it means a pilot signal will be reached as a sphere wave, not plane wave. So in this case, what happened? So if we can create the conjugation of the amplifier. Of course, conjugation doesn't mean the conjugation of the amplifier. It means when we receive the high power at the center of the receiver, for example, we reduce the power at the center. At the edge, due to the long path length, received power decreases. It's a sphere wave. And in this case, we emphasize, we amplify the transmitting signal compared to the weak received pilot signal. So we named it amplitude conjugation. And as a result of the amplitude phase conjugation, we can increase the received power. And this is a result of the simply phase conjugation retrodirective only. Compared to this result, it's better. The amplitude and phase conjugation system is better. So it's our Kyoto University original technology. And at last, we combine multi-user, multi-path. So of course, it's easy to understand. We can apply this multi-pass, multi-signal retrodirective. So here you can see it's better than the other beamforming technology. So this is a very interesting result. So I don't have enough time. I skip this. So now I have 8 minutes more for question and comment. So that's all my talk today. So today you've already learned how to increase the beam efficiency in front user case. And next, when the user moves, we can control the beam direction in the afternoon lecture. And at last, when we control the beam direction, we must detect the position of the target. And now I explain the technology of the target detecting. So today, now you can develop very good retrodirective system, beaming retrodirective system with high efficiency with help of the phase array or the retrodirective system. So that's all my today's talk. Thank you so much.
Thank you very much.
So I believe there is no question. So,
Any query? No. Okay.
yeah, so even with today's lecture, you can be a good antenna engineer. But for wireless power transfer, as I mentioned yesterday, we have to consider the combination of the antenna technology and the circuit technology. So tomorrow and the day after tomorrow, I will introduce the circuit technology. Tomorrow, I will introduce a transmitter technology, and the day after tomorrow, I will introduce a receiver technology. It's similar to the Professor Khan's lecture, but more deep technology of the receiver day after tomorrow. Totally, you will be the good engineer of the wireless power transfer.
Okay, with this, we should conclude this second day of this GYAN course. Let's give a big round of applause for all three wonderful sessions delivered by Professor Naoki Shinohara. And hopefully tomorrow we will have as per schedule. Okay. See you all tomorrow morning at 10 o'clock.
Tomorrow.